is where we'll start looking at double integrals and so on, and this will actually take up a fair chunk of the course. And in fact, that will be the remainder of my lectures on multivariable calculus, so on the double and so-called triple integrals, or you could just call them multiple integrals. But before we get on to that, we're going to cover this chapter 6 of the workbook on hyperbolic functions. Actually, it's a topic that, in my opinion, is more suited to the course Math 1051 that we offer in first year. In fact, really, it's some of you who have done that course may have come across these hyperbolic functions in some of the homework exercises or tutorial sheets. I always talk to Victor Sharashkin about this, who lectures Math 1051, and yeah, he says we never cover it in lectures, but sometimes we give them as homework exercises. The reason we're putting it in Math 2000, I mean, we did this a few years ago. We just included this as a one sort of standalone lecture because we realised students were getting through our early level math courses, including Math 2000, not knowing what hyperbolic functions were, and then getting onto courses later on where these hyperbolic functions were just being used. They were being thrown all over the place, and students were saying, "Oh, what is this? I've never seen this before." And so we decided, we have to squeeze it in somewhere, so we'll have a lecture on it in Math 2000. Now, there's really not all that much to this lecture. All right. In fact, in this chapter, a lot of the topics that are covered are all about developing your familiarity with these new types of functions. But in actual fact, they're not all that new. They're really just defined as an alternative to exponential functions, and in fact, they pop up in differential equations quite a lot. Now, there's a question on the assignment, question 2, part D. So question 2, I think it's question 2. It's this one where I introduce this concept of normalized solutions of a homogeneous linear equation. And so I give one example. And basically, for that question, parts A, B, and C are just walking you through that concept and developing the concept. And part D says, here's another equation, find a normalized set of solutions. It turns out the answer to part D is a set of hyperbolic functions. You should realise that if you've already worked through that problem. So all this material that we'll see today is covered in the Stewart textbook from page 462. So it's in the section, I think it's in the section on functions, or maybe even inverse functions, because we'll have a look a bit later on about the inverse functions of these hyperbolic functions. So really it's just about developing some familiarity with this or with this family of functions that are very commonly used in advanced maths and engineering courses. So the definition of these functions is very simple, and what you'll see throughout this lecture is a parallel between the trig functions, right? So you'll see why we use these names, because of the similarities with their trigonometric counterparts. So here are the first two hyperbolic functions that we'll define, so-called cosh and sine functions. Actually, it really depends where you come from. I spent a few years overseas working as a postdoctoral researcher, and I just found a lot of people, rather than say call this shine, they would call it cinch. So I mean, it depends where you're from. So cosh or cinch or shine or whatever you want to call it. Actually, you'll see later on some of the other functions we define. It becomes a little bit of a mouthful, but anyway. You can see, so the H that we've tacked on to the end of COS and SIN the H stands for hyperbolic, right? Maybe you can you can see that. So there are these new functions, cosh and shine, which are just defined as linear combinations of these exponential functions, right? So cosh is just e to the x plus e to the negative x on 2, and shine is the difference between those divided by 2. All right, but why do we use this? Why do we call them cosh and shine, so something similar to the trig functions? Well, one thing you can do just by direct calculation is verify that, this is just by using the definition, right, in terms of these exponential functions, you can verify that cosh squared of x minus shine squared of x equals 1. And it's at this point I just remind you of that well-known trig identity, cos squared theta plus sine squared theta equals 1. So there's one of the first parallels, I guess, between these hyperbolic functions and their trig counterparts. All right, a subtle difference though. This one has a minus sign, so the difference of cosh squared and shine squared is 1 rather than their sum. All right, so really, after I've defined these cosh and shine functions, I could stop the lecture there and say that's hyperbolic functions. Everything else that follows is by analogy with trig functions, right? So, for example, once we've defined the trig functions cos and sine, how do we define functions like tan, the tangent function, the cotangent, the secant function, the cosecant, and so on? We do it in exactly the same way for the hyperbolic functions. All right, but why do we call them hyperbolic functions? What does this have to do with a hyperbola? Well, firstly, let's just recall what this trig identity tells us. Right? In particular, this comes in very useful for parametrizing circles. All right, so, or in particular, parametrizing the unit circle, if we set x equal to cos of t and y equal to sine of t, this is actually describing, so in the xy plane, it's just describing any point on the unit circle. So say with coordinates cos t and sine t, and where t is allowed to roam over a domain between 0 and 2 pi. All right, so the trig functions are very useful for parametrizing circles. Well, guess what? These hyperbolic functions are very naturally associated with hyperbolas in the following sense. So if we decide to parametrize or introduce a parametrization so that x equals cosh t and y equals shine t, so that identity that we can derive, that hyperbolic identity, cosh squared minus shine squared is 1, can simply be written as x squared minus y squared equals 1. So this actually describes, in the xy plane, describes a hyperbola, so with these asymptotes, y equals plus or minus x. So here are the two curves. In fact, it parametrizes just the right branch of this hyperbola. So over this side, any point on this side can be expressed as, or parametrized by cosh t and shine t. So hence we call these hyperbolic functions. All right. There's also another curious parallel between these hyperbolic functions and indeed the argument they take on. Going back to trig functions, if you have a look at, if you parametrize the unit circle in this way, so this shaded area is just given by t on 2. Okay, I mean, it makes sense if you think about the area of the unit circle being pi. Okay, and if the t roams over values from 0 to 2 pi, you cover the entire circle, you get a half of 2 pi. So you you do certainly expect that when you take the appropriate fraction of the whole circle. But it turns out it's also possible to show that this area in here is also t on 2. So there are these parallels between these hyperbolic functions and the trig functions. So we use that language. We call them, well, we can't call them cos or sine, but we call them something similar, right? We use symbols which are similar for these functions. So call them hyperbolic cos or hyperbolic sine, or just cosh and shine. Incidentally, the derivation of this result for hyperbolic functions is given in Stewart on page 469. I think it's in an exercise, one of the exercises, or question 70. They walk you through this calculation. Okay, so I suggest having a look at that. So remember, this lecture is all about gaining familiarity with hyperbolic functions. By the end of this lecture, what I'm hoping you can do, or at least once you've seen all this material, I mean, some of it might take a while to set in. I've put up a problem sheet with some nice examples on hyperbolic functions. So I've put that up on the on Blackboard this morning. This isn't the assignment, by the way. These are just the problem sheets. I've uploaded questions and solutions on hyperbolic functions. There's just a handful of them. That'll also help you develop your familiarity with these. But certainly by the end of all this, what my hope is that you have the same working knowledge of these hyperbolic functions as you do now with the trig functions. Okay? And so, so that's what this is really all about. Okay, so we've already seen a few similarities with the corresponding trig functions. Well, what about the derivatives? Okay, what about derivatives and defining other functions? Well, compare these derivatives. I mean, you can just evaluate this just using the definition, right? When I say using the definition, I mean going back to right at the top of the screen on the other, on page 37 here, the definition of cosh and shine in terms of the exponential functions, right? Exponential functions are very easy to differentiate, and so if we do that, we can see immediately that the derivative of cosh is shine, and the derivative of shine is cosh. Okay, you can work that out straight away just by differentiating the exponentials. Now, just compare this with the trig counterpart. So there's always this subtle difference, right? The derivative of the trigonometric cos function is negative sine, and the derivative of sine is cos. Okay, so there are similarities, but it's just slightly different. They're always out by a sign here and there, by a factor of -1 here and there. Okay, so there are other similarities, right? Cosh of 0 is 1 and shine of 0 is 1. Very much like or exactly like the corresponding trig functions. And what's more, cosh is an even function, so that implies that cosh of -x is equal to cosh x. And the shine function is odd, so that, in other words, shine of -x is just negative shine of x. Okay, so we use the way we define these other trig functions to define corresponding hyperbolic functions. For instance, the trig function tan is the ratio of sine and cos, right? It's defined as sine over cos. So in this case, hyperbolic tan we'll define as hyperbolic sine divided by hyperbolic cosine. All right? So in other words, here we define the function tanh, I guess, or some people I've heard refer to this as than. I prefer tanh. So the tanh function is just the shine over cosh. See, it's a mouthful. The cosh function is cosh over shine, and we have other functions. Sech, as 1 over cosh x and cosec of x as 1 over sine of x. Okay, so I guess one thing, I don't want to spend too long talking about this, but one thing when we meet new functions, it's always nice to introduce ourselves, get to know the function a little bit, but also to work out the domain and range of those functions. This is something that's always important, especially whenever we make use of these functions. We just absolutely must know about their domains and ranges. So I don't want to spend too long, but in just these next couple of pages I've provided a couple of graphs, and perhaps, I mean, you could get onto something like Wolfram Alpha on the web and just have a look at what some of the other graphs look like that are not in the workbook here. So for example, the cosh function being a linear combination of those, remember this is e to the x plus e to the negative x on 2, being a linear combination of those two exponential functions. You should be able to work out that in this case, cosh of x is defined for any x, but only takes on values greater than or equal to 1. In other words, we can say that the domain for cosh is just the set of all real numbers, but the range is just the interval from 1 inclusive, well, all real numbers greater than or equal to 1, which I could write as this interval. Okay? And similarly for sine, okay, we can also work out for sine the domain and the range, in fact, is just the set of real numbers. All right, and remember this is the difference. So just rewriting the definition here, remember sine is the difference of those exponential functions, e to the x and e to the negative x. So over the page, so just quickly, it's probably just worth at least writing out what the domains and ranges of these functions are, although you may be able to see it by inspection of these graphs. And you could work it out using the definition of tanh and cosh, as I've given on the a couple of pages previously. So the tanh function's defined for all real numbers, but only takes on values between -1 and 1, so not including those endpoints. So all real numbers between -1 and 1. All right, and for cosh, the domain is a little more complicated. The domain we can actually write as the union of two intervals, namely the interval of all the negative numbers, so that is not including 0, and all the positive numbers. Right? So we're not including 0 in that domain, because cosh is actually the cosh over sine, and at 0, sine takes on value, takes on 0, so it's not actually defined at 0. And the range in this case, it takes on values from negative infinity to -1, or actually not including -1. So it's the union of that interval and a similar interval. So all real numbers strictly greater than 1. All right, we can also define their inverse functions. And I might actually, I might leave it as an exercise, in fact, just for you to work out what the graphs of sech and cosec look like and what the corresponding domains and ranges are. We can also define their inverse functions. Now just, well, in MATLAB, for example, these inverse functions referred to as follows. So A cosh for the inverse cosh function, A shine, and so on. All right, but here I've written, so a lot of the literature will refer to them as R cosh or R shine, R tanh, and so on. My tendency is to write cosh to the -1 to denote the inverse function. And I'll just point out that this is not the same as 1 on cosh. So, for instance, 1 on cosh. And in fact, this is why, I'll just point out, this is sech, for example, 1 on cosh. So it's different to 1 on cosh. This is the inverse function. All right, and similarly, I'll use shine to the -1, tanh to the -1, and so on to denote the inverse functions. Okay, so what about defining the inverse of the cosh function? We'll have a look at the graph of cosh here. Since we know the domain is all real numbers, but the range is only from all real numbers greater than or equal to 1, in order to define the inverse function, we're going to have to restrict the domain of cosh in order to define that to be an invertible function. So, for example, the problem is if I were to think of plotting, or think of just flipping this graph round, or rather looking at the reflection of this graph about the line y equals x, this is what it would look like, including both sides of the cosh function, right? Including both positive values of x and negative values of x. So if I was just to take this graph and flip it so its mirror image would look something like that, including this dashed line, right? But if I want to use this to define the inverse function, if I choose this point here, and now that's my input, I want to define the inverse function, well, what's the output going to be? Right? So which one do we choose, right? The diagram I've got there, including the dashed line below the x-axis there, it doesn't define a function, right? It doesn't pass, what do you call it, that vertical line test. It doesn't pass that vertical line test. We need a unique output in order to define a function. So in order to do that, we restrict the domain of cosh to just real numbers greater than or equal to 0, or in other words, to that interval from 0 to infinity. So if that's the domain of cosh, then that implies that the range of the inverse function, cosh inverse, is now the same as that restricted domain. So as the interval from 0 to infinity, or just real numbers greater than or equal to 0. And the domain of the inverse function is just that range of cosh, right? So all real numbers greater than or equal to 1. Okay, just as an analogy, perhaps, in thinking why we have to restrict the domain. I mean, you can start to see why in this lecture, why I said at the start, perhaps this is more suited to a Math 1051 lecture. But nevertheless, if you just confer with the example of, say, y equals x squared, all right, compare this. I mean, it's a similar idea, right? If you want to define the inverse function of this, it's actually the square root that we want, right? But when we define the square root, that inverse function, do we take the positive root or the negative root? Well, we just restrict our domain so that we take the positive root, and here's y equals positive root x, right? Whereas if we included the negative root, that would be down here. Okay, but that's y is negative root x. So when we take, for example, y equals x squared, and we take the square roots of both sides, so that implies that x is plus or minus root y. So we actually have two choices, is what I'm saying. So we have to restrict the domain in order to define the inverse function. So I'm just making a comparison to cosh and the function x squared. All right, well, a simple idea anyway. And, well, over the page, I won't say too much about these, but I've just got the graphs of the inverse sine function and the inverse tang function. Okay, one thing that we can use these hyperbolic functions for is in substitutions when we evaluate integrals, or particularly definite integrals, not just antiderivatives. But we can use it in the substitution method. So I'll just actually, well, I'll show you how to use that in a sec. But first, what we can do is work out what the derivatives of these inverse functions look like. So, for instance, the inverse sine function, y equals, so as I said, I always like to write sine to the negative 1. We can actually work out the derivative of this explicitly using differentiation. So what I can do here is rewrite that equation. If I've restricted the interval, I can rewrite that equation, restricted the domain of sine in order to define this inverse function. Then that implies that the relationship is that x equals sine of y. Okay, and then I can differentiate both sides with respect to x. So that is both sides of this equation with respect to x. All right, so that implies, so on the left-hand side, I'll just have d by dx of x. Now I'm assuming, well, we've defined y as a function of x. It's actually the inverse function. And what we want to know, so we want dy dx, right? Because that's how I've defined y. Okay, and y is a function of x. So on the right-hand side, I've got d by dx of the sine function. But now here we've got a function of a function. Right? Sine of y, y is a function of x. So in order to differentiate that right-hand side, I'll need to use the chain rule, okay? Because I've got a function of a function. So on the left-hand side, dx by dx is just 1, all right? But now on the right-hand side, I'm going to have to use the chain rule, all right? So y is a function of x, so that'll be dy dx multiplied by d sine y dy. Okay, which is just, so that's just dy dx times, we know the derivative of sine is cosh. Okay, we've seen that earlier. All right, so now remember we want dy dx in this calculation, so if I just divide through by cosh y, so that implies dy dx is 1 over cosh y. Well, what I've done here is just say, oh, this y equals inverse sine of x satisfies this first order differential equation, right? Okay, well, that's not exactly what I had in mind, but I know there's this hyperbolic identity satisfied by cosh and sine. So I know that cosh squared y minus sine squared y equals 1. And so I can simplify this by isolating cosh y. So that implies cosh y is, so just manipulating this equation here, what do we have? Cosh squared is 1 plus sine squared, and then take the square root. But I would have to take the positive square root since we know cosh of y is always greater than or equal to 1. So I'd have to take the positive square root. Okay, so I'll just make a note of that. That must be greater than or equal to 1. Okay, we worked out the range of cosh earlier on, or we saw what the range was earlier on. Okay, but just going back to the top, I've written it in a little box here. Shine of y is x. Okay, so this is just square root of 1 plus x squared. Okay, and so now that implies that dy dx is just 1 on square root of 1 plus x squared. Okay, so we've shown that result. So as I mentioned, we can use these hyperbolic functions to evaluate some antiderivatives and to use as a substitution in some definite integrals. So here's just a couple of examples where they come in useful. So I'll call this one A and B. So there are two. The first one, A. What we'll do, and it all comes from the form of that hyperbolic identity, right? It all comes back to the form of this cosh squared minus shine squared equals 1. I mean, in a very similar way to how we use the trig functions in a substitution to help us evaluate antiderivatives of some given functions, right? In fact, in some cases you find you have a choice. You can either use trig functions or hyperbolic functions. Sometimes you can use logarithms, and so on. But here, this is just expanding your toolkit and to help you become familiar with hyperbolic functions. All right, so just in this. For this first integral, we'll set x equal to shine t. So that implies in the integral, when we make our substitution, we can more or less replace dx with cosh t dt. I mean, just observing that dx dt equals shine t and using that as a substitution in the usual way. So that implies the antiderivative of 1 over square root of 1 plus x squared can now be written in terms of this new variable t. So the dx, so that's just cosh t over, and now I'm setting x equal to shine t, so that'll just be 1 plus shine squared t inside the square root, and then integrating with respect to t here. All right, but from that hyperbolic identity, I've written it on the previous page, the cosh squared minus shine squared equals 1. We can rearrange that and see that in the denominator here inside the square root, we end up with a cosh squared. Okay, so we end up just having to write down to work out the integral of 1 with respect to t, which is just t plus a constant. But remember, we've set x equal to shine t, and so this is inverse shine of x plus a constant. Right? This is actually just the reverse calculation of what we've just shown on the previous page, in fact. Okay, and for B, so right at the top of the screen there, this one's slightly more subtle, and in fact, I should point out that if we're wanting to integrate 1 over the square root of x squared minus 1, I mean, first thing to observe is, well, I can't be talking about values of x between -1 and 1. For example, if I substitute in x equals 0 into this function, I end up with the square root of -1, right? So this doesn't make sense in the real world for x defined between -1 and 1. So just at the outset, I'll assume that for b, I'll assume that x is strictly greater than 1, and then this function makes sense, and the antiderivative makes sense on that interval. And so I'll just point out that you should always be mindful of your domain and range when using substitutions. Especially if you have a definite integral. So, for example, if this integral in part b were a definite integral, and say it's asking us to integrate from -10 to -8, then clearly this assumption I made is not suitable, right? Saying that x is greater than 1. But in that case, I could assume that x is strictly less than 1, and possibly work with a different substitution. Okay, anyway, it's just something I should make you aware of. I mean, many of you who have done Math 1052 would be very familiar with all the different techniques of integration, including substitutions, and taking care when choosing your domain of the substitution, right? So anyway, it's just something to keep in mind. So for this one, we see we've got an x squared minus 1 inside the square root. So we'll set x equal to cosh t in this case. And so we know the derivative of cosh is sine, right? Positive sine, right? That's where it differs to its trig counterpart. So that implies that in the integral, so differentiating dx dt equals sine t. So this we can just replace with sine t dt. So that implies that the integral that we have of 1 over square root of x squared minus 1 is just making all the substitutions. We'll have sine t divided by square root of cosh squared t minus 1 dt. All right, and so just in the same line, I'll write this as sine t on the square root of, so using that hyperbolic identity, we've got the square root of sine squared t. All right, so just to highlight that point, I know we've assumed that that x is greater than 1 here, but when I make this substitution, x equal cosh t, so one thing, I'll just put the graph up, remind you what cosh t looks like. Okay, so we're assuming that, well, imagine this is cosh t, and so t along the horizontal axis, this is cosh t. So cosh t is clearly greater than or equal to 1, but you can see in order to do that, I can take negative or positive values of t. So I have to be a little bit careful when I work out this square root of sine squared. The temptation is to immediately write down sine of t. Let me just put a little star here as a word of caution, and I'll come back to that. Okay, so let's just proceed and do that and write the square root of sine squared t as sine t, and then clearly the sines cancel, and we end up with integral dt, which is just t plus a constant, and we end up with this antiderivative being inverse cosh of x plus a constant. Right? And remember, this is for x greater than 1 that I assumed at the start. All right, but let's come back to this discussion about this this caution that I've made up here. All right, and I guess that's the caution going from this step down to here, and that is in particular in writing the square root of sine squared t as sine of t. So there's a convention, right, that the square root is always positive, right? When we write the square root, we mean the positive square root. And we usually distinguish between that and the negative square root by writing a negative sign in front of it. Okay? So that's the convention, is that whenever we write the square root of something, it's always a positive number. Okay? So what about the square root of sine squared t? Does that always equal sine t? Well, here on this same page on the other screen, I've got the graph of sine t, and one thing you can see is that it takes on negative values when the input is negative. Right, so to answer this question, I can say, well, it does, but only if t is greater than or equal to 0. Right? What if t was negative? Okay, if t was negative, then sine t would be negative as well, right? And that would break this convention of the square root always being positive. So, in that case, for t less than 0, sine of t is also less than 0. And so that implies that when we take, using this convention that the square root is always positive, when we take the square root of sine squared t, in this case, so for t less than 0, we would have to write negative sine t. All right, so if t is less than 0, sine t is negative, and then negative sine t is positive, adhering to the convention. There was a question just here. You're squaring it here, okay, but I want to write this square root of sine squared t as a number, okay? I want to write that as a number. So say t was negative 10, okay, and I work out sine of negative 10, that's going to be a negative number, right? So if I then write the square root of sine squared of negative 10, sure, it's the square root of a positive number, but it's a positive, that square root itself is also a positive number. So because sine of negative 10 is a negative number, to stick with that convention, I'd have to multiply by negative 1 here, right, to make that positive. All right, it's a subtle point, right, but it's something that you do have to be a little bit careful of, especially if you're dealing with definite integrals. And especially definite integrals that take on negative values. And so you always have to be mindful of your domain and range when you use these substitutions. Okay, so just over the page, actually I won't go through this calculation because this is very similar to what we've just been through. So on page, so this is very similar. I'll leave this as an exercise. And it's similar to the calculation we've just done on page 43. So on page 43, we worked out the derivative of the inverse sine function. And so now on page 45 in the workbook, it's just asking to do a very similar calculation with the inverse tanh function. So I might just leave that as an exercise. But there is something else very important on this page, and it's just making parallels between these inverse hyperbolic functions and the natural logarithm. Now, let's go right back to the first slide I had up, where I defined cosh and sine, and I defined them in terms of exponential functions. So actually, if I then went on to define the inverse functions of those, right? And now it should come as no surprise. If we define cosh and sine in terms of exponential functions, perhaps it's no surprise that their inverse functions are defined or can be written in terms of the inverse function to the exponential. The inverse function of the exponential being the natural logarithm. Okay, and so it turns out we have all these parallels, all these connections between these inverse hyperbolic functions and the natural logarithms. I think actually one of the assignment questions might be to show this first one. I can't remember which one. I definitely set one in question 6 maybe 6 part A. I think it was the inverse tanh function. So proving this, this identity so that the inverse tanh function is related to that natural logarithm. So instead of working through your assignment question for you, let me go through another example. Let me go through the inverse Shine function and show you the sort of calculation that's involved. So, all right, we'll define y to be this inverse Shine function. All right, and so that means then that we can write x as Shine y, but remember how we define Shine y. Okay? So on the right-hand side, Shine y is just defined in terms of exponentials. Remember, that's just e to the y minus e to the negative y on 2. So if I multiply by 2, I get 2x equals e to the y minus e to the negative y. And now if I multiply through by e to the y, and just put all the terms over onto the left-hand side, or rather I'll put them all over to the right-hand side for convenience. We end up with e to the y all squared. So that's from this term. Then we'll have a minus 2x e to the y coming from this term, but moved over to the other side. And then we'll have a minus 1, and that equals 0. So this is actually quadratic in e to the y, and what we want to do is isolate e to the y and then take the inverse of that. So that'll be a way of introducing the natural logarithm. So I'll just say solve for e to the y, so it's quadratic in e to the y. So that implies then we could just rely on the good old quadratic formula. So that's 2x plus or minus square root of, so 4x squared minus 4 times the coefficient of the square term times the constant term, which is negative 1 in this case, all divided by 2 times the coefficient of the square term. All right, so this is this now simplifies. So I've got a common factor of 4 here inside the square root, which I can bring outside. Square root of 4 is 2, and both these factors of 2 in the numerator cancel with the denominator. So we end up with x plus or minus the square root of x squared plus 1 in this case. Now I've got 2 choices here, 2 possibilities. So we'll just note that e to the y is always positive. But if I were to choose the minus sign here, if I was to choose x minus square root of x squared plus 1, so note the square root of x has the same magnitude as x, but the square root of x squared plus 1, its magnitude will be just a little bit bigger than x, right? So x minus something bigger than x will give something negative. Okay, so I'll say this is less than 0, and therefore we must have e to the y, we must choose the plus sign, so we must have e to the y is just x plus square root of x squared plus 1. Oh, and then I take the natural logarithm of both sides and end up with y is log of x plus square root of x squared plus 1. Okay, so that's the sort of calculation I'd expect in your first in assignment 1, question 6, part A, I think it is. Just one more observation I just want to make. I'll finish the lecture with this thought. There's this completely reckless formula known as Euler's formula, relates the exponential e to the plus or minus ix with these trig functions, right? Cos x plus or minus I sine x. Some of you may have may have seen this before. Absolutely brilliant formula. Love this one. So, what if we now allow imaginary or complex values to be input into these hyperbolic functions? So, for instance, if we take cosh of ix, right, I the imaginary unit, we have e to the ix plus e to the negative ix on 2. That actually simplifies to cos x. So we now allowing for complex numbers, we have this direct relationship between the trig functions and the hyperbolic functions. And similarly, sine of ix is just the pure imaginary I times sine x. So there's this relationship between the trig functions cos and sine and the hyperbolic functions cosh and sine once we allow complex numbers. So just a nice little connection there, making yet another parallel between those functions. All right, so next week, guys, we're going to start the calculus part of the course. We'll start multiple integrals. Oh, and from page 47, there's just some reading on a very famous historical problem known as the catenary problem. So that is just chain hanging under gravity that is related to the origins of the hyperbolic functions. Okay, I'll leave you with that thought, but I'm not going to go through that in lectures.